As announced on Classum, if you're not happy with your grades, or if you attain too high on AUPRC and you got a, and you think you think you've done everything right and you deserve a 2.5, then please let me know. So there were a couple of students uh, who actually spent a lot of time on feature engineering and actually achieved like really high AUPRC uh, without any information leakage from the future or any cheating or anything. So if you think you are that people, then please let me know, and we can discuss whether you did everything right and all that. 네, 그 방금 전에 말씀드린 대로 그 AUPRC를 이제 0.4 이상이면 일단 감점을 하긴 하는데, 그거는 그 피처 엔지니어링이 별로 이렇게 상식적인 수준에서 피처 엔지니어링을 하면 보통은 0.4 이하가 나오게 되거든요. 이제 엄청 높은 분들이 간혹 계신데 그분들은 실제로 피처 엔지니어링 시간을 엄청 쏟으셔가지고 이제 높이 나오신 분들이 조금 계셨어요, 몇 분. 그래서 그분들은 다 제대로 점수를 받으셨거든요. 이제 자기가 그런 경우에 해당하는 것 같다, 그러면은 알려주세요, 저한테. 근데 대부분의 분들은 제가 보니까 한 뭐 0.4 이하인 것 같긴 해요. 네, 그런데 뭐 0.8이 나왔다, 이제 그건 뭐 빼도 박도 못하는, 네, 그냥 뭔가 뭐 인포메이션 리키지가 있거나 아니면 그 레이블을 잘못 설정하셨거나 뭐 그런 것 같습니다. All right, and next time, maybe next week, we can invite a couple of people who actually did achieve a very high AUPRC scores, and they can share what they did to achieve that kind of like that level of AUPRC. So yeah, they actually done like feature selection and a lot of pre-processing with the chart event features, and actually they use extra features from the patients or the admissions table. So maybe I can ask a couple of students to share their experience overall, and so that everybody can learn from their experience. Right, and all right. Okay, so I think that's probably it. All right, let's get started then. Oh, by the way, I uploaded the slides on Classum maybe an hour ago, so please, if you want to, you can go download the slides right now. All right, week 7, concept representation. This also will be not that long, not that long. So that next week we can dive right into the domain knowledge and graphs. So this will be a bit of like a preliminary stuff, because these days a lot of researchers actually try to incorporate domain knowledge or graphical or knowledge, like DAG-based, DAG being the directed acyclic graph. So DAG-based domain knowledge or DAG-based ontology, medical ontology, combine them with EHR to learn better representations. So it would be better to actually just skim through what representation learning is, even though we are already quite familiar with representation learning in vision and NLP. Maybe not everybody's familiar with the concept in the healthcare. So this will be a bit of like a basic overview. Right, so previously we've looked at interpretability, and so we took a look at the linear and non-linear model versus non-linear model, and then the three different ways to interpret your model, a prediction model, which were gradient-based approach, such as CAMs or grad CAMs, or integrated gradients are also okay, and or I haven't gone through more recent ones like layer-wise relevance propagation, which is LRP, something like that. So those, or looking at the filters, all those were like more or less gradient-based approach, usually used by computer vision models. So that was number 1. Number 2 was neural attention, and we actually took a deep dive into retain, which is a completely interpretable model using attention to make sequential decisions. So we also discussed whether attention is actually an explanation, and that was still up for debate. The last one was model agnostic approach. So we took a look at 2 representative examples, which were Shapley values and line. And those who are interested, they can look more deep into this topic, model agnostic approach topic, and take a look at papers such as Deep Chap or that kind of stuff. All right. Any question with the interpretability? Or actually, any question with the project scores? Yeah, yeah, the criteria was actually really maybe too generous, but still, it's just more or less a practice for everybody. So no point in actually trying to make like a harsh criteria to, so that everybody can suffer. So. All right, so if there are no questions, then we'll move on to the concept representation. So today's topic is, what is representation? I mean, everybody should be familiar with this, but we'll just go through it anyway. And learning representation for continuous input and discrete input. So that's actually the motivation. And then we'll take a look at skipgram for healthcare. So skipgram is actually used for NLP, especially learning word vectors, word embeddings. But you can directly use skipgram for healthcare as well. And then we'll take a look at something called METUVEC, which is a bit more advanced, which is like a skipgram based healthcare concept representation model, but a bit more specialized for EHR structure, right? So what is representation? Representation is a representing an entity as a vector, because in order to make a prediction, or actually not make a prediction, to do anything, in order to do anything with your data, you need to vectorize it into a fixed size vector so that you can plug that into any model. It could be random forest, support vector machine, logistic regression, even feed forward network, or ConvNet, whatever. I mean, some models don't really care about the size of the input, such as RNN, or actually like purely convolution-based image models such as ResNet. Like in that case, you can, and for example, like ResNet can accept any sized image, and it'll just adapt to that, and the output will be the output size will be adjusted or be determined by the size of the input. So some models don't really care about the size, but usually we try to represent your input, our data, as a fixed size vector, so that we can do whatever, like predict or compare or compress, or or generate, whichever you want. So for example, images can be represented as a sequence of pixels. So if this is a 128 by 128 image, then you'll have a 6. I'm sorry. I think there was slight error with the Wi-Fi. Some kind of hiccup. All right, back to the slide. So okay, so as I was saying, this would be represented as a 16,000 dimensional vector, where each dimension represents a pixel intensity. So this will be a continuous input, and the same goes for all kinds of modalities, not just images, but maybe your audio wave, your speech can be represented as a vector as well. So it'll be a one-dimensional, and depending on the sampling rate of your of the data. So usually it's like 16,000 or like 256 actually no 256,000 sampling rate, something like that. So depending on the sampling rate, that will determine the length or the size of the vector, but it'll still be a vector, and each dimension represents a pitch in that time step. So that is also a continuous input. Words or text are a bit different. So words or text are discrete. So for example, if you want to represent this sentence as a bag of words representation, then you would have to prepare a vocabulary of dictionary, which contains all the words that could occur in the text. For example, let's say that your vocab is like 50,000. There are 50,000 words that could possibly occur in your given text. So you prepare a 50,000 dimensional vector, then you count how many words in each dimension occurred in your given sentence. So for example, here, let's say, actually, is this all unique in like here, yeah, like the word the occurred twice in this sentence. So maybe this is that the, and then like the zeros are the ones that didn't occur, and the ones are the ones are the words that occurred only once. So this can be represented as also as a vector. So, but this would be unlike these two previous examples. These are uh, actually discrete input. So discrete it has it's a discrete representation, and this is fundamentally different from. So the words are fundamentally different from these two. So these are actually pixels, image pixels. So they are actually just natural signals. It's like photons. Like images can be capturing the photon intensity, and the audio waves might be capturing like the patterns in the air, like the or the uh well, I forgot what I forgot what 진동 was in English actually. 예, 네. 그 이제 그 공기에서의 진동을 캡처하는 그런 거가 이제 그 오디오 웨이브에 해당을 하겠죠. So that would be, I forgot what, actually let me look it up. That's hmm. Oh, vibration. Yeah, actually, yeah, that was stupid of me. Oh, did I actually? I'm sorry. Yeah, vibration in the air. So that would be so this kind of wave signal could be capturing the vibration in the air that was made by your vocal cords. So that is also a natural signal. So they are, so actually, like deep learning models, or actually just all these kinds of machine learning models are really good at capturing the representation of the natural signals. But the words are actually not natural signals. They are made up by people. So it's a human-made signals, like the word to or rose or diverge. Like they don't mean anything in nature. Like they don't come from the nature. It was invented by people. So it already has a lot of semantic meaning embedded inside each word. Like two has a meaning. It's a very abstract meaning. It comes after one. And roads or diverged or would, travel, difference. These are all, they have a meaning that only people can understand. But waves or images can be understood even by animals because they are natural signals. And so far, deep learning models, until like maybe 2017, 2018, deep learning models were really good at capturing this kind of signals, like images or like audios and that kind of stuff, but not so much with the words. But these days, thanks to BERT and all the transformers and GPT-3, it seems to be the case that maybe deep learning is now actually conquering high levels, conquering and capturing the high level semantic concepts as well. But yeah, we'll have to see. All right. So as I was saying, yeah, just like ultimately, just like these three examples here, like images, audio waves, sentences, healthcare records should be represented as a vector, and that's what we've been doing so far with predictive models. So once we had the visit information, or actually ICU stay information, and we had to transform them into a thick size vector to put them into logistic regression or RNN for that matter. And that's what we've been doing so far. So that is this a 40,000 dimensional vector is a representation of a single visit. So which is again capturing a discrete information, just like this, just like sentences or text. This is a purely discrete sparse binary vector. So this is completely different from the pixels or the audio waves. So that is why a lot of healthcare models or healthcare research directions are very much tightly connected with NLP techniques, because a lot of things are a lot of concepts or a lot of data are discrete concepts in healthcare, just like the words in NLP. So continuous input, yeah, for example, what we can do is, what we can actually try to see what kind of representation is learned by the model. For example, like we'll just take a look at the image example. So let's say that you have a stacked autoencoders, which are actually really old models these days. These days, not a lot of people use stacked autoencoders or restricted Boltzmann machines to classify images. But that used to be the case back in 2009, 8, like even before like AlexNet. So even before AlexNet, like Jeffrey Hinton and their students try to, or Yusha Bengio's students, they try to use stacked autoencoders or stacked RBM, stacked restricted Boltzmann machines to classify images without any feature engineering. And they actually did show some success, but then in 2012, AlexNet came along and then just conquered everything. But anyway, so let's assume that this is a stacked autoencoder. So autoencoders are usually just there's an encoder and decoder, but then what we can do is we can stack encoder parts. We can stack a lot of layers for the encoders and then try to train each layer in a layer-wise manner. Like you have a single layer, we train it to compress it into a lower dimensional space, and then using that lower dimensional space, we train another layer to even compress it into even lower dimensional space. And then we can do that multiple times to actually represent a 16,000 dimensional pixel image into maybe like 256 or 128 dimensional vector. But you have to do it in a repetitive manner. You can't just compress a 16,000 dimensional image into a 128 dimensional vector at once. You should do it in a increasing manner, and that's what stacked autoencoders are or used for like 20 years ago. No, not 20 years ago, maybe 10 years ago. So once you've done that, and then you have let's say that there are 3 heads. So this is a classifier for person, cat, or dog, and then you have an image. So you have input pixels. So you put like in pixel intensity. So there should be actually 16,000 x's, x1, x2, x3, all the way to x 16,000, and then you incrementally compress it into lower dimensional space, and then there will be 3-way softmax classifier at the end. And so these are the output probabilities. And what we can do is we can try to see what the model has learned by trying to maximize, trying to figure out which feature or which input maximizes the probability of a person. So this would be actually using the gradient-based approach for interpreting the model. So interpreting the model can have multiple meanings. Like if you're using attention, what we're trying to interpret is how the model arrived at the final decision. So that is usually what attention is used for, because what attention indicates is the importance of the features that derive the final output. But when you're using gradient-based approaches, like trying to generate or trying to learn a image or input that maximizes a certain output, that is actually trying to learn the latent representation learned by this model. So for example, if you want to, you can actually do like a backprop while treating the input as a parameter. You can do a stochastic gradient descent with respect to the input that maximizes this output, this red output. And if you do that, then certain pixels would have higher contribution, or certain pixels would be lighting up, and certain pixels would be dying down in order to maximize the person class probability, right? So that would be this guy. So this is really old material from way back in like 2014, 2013 by Google Brain, when actually Professor Andrew Ng was collaborating with Google Brain to do like really large convolutional neural network models. And what they found out is that if you try to maximize a person output, and then you can see what this model understands as human face, and that is this. So this is a representation of the typical human face. Like that, if your input looks like this, then your model would actually, classify this as a human or people. And if your input looks like this, so this is a representation of the cat. So this input is the input that maximizes the probability of the cat class. So this is the one that maximizes the human class. This is the one that maximizes cat class. And you can see that that is actually capturing the essence of cat pretty nicely, in my opinion. And if I remember correctly, what they did is they actually crawled like millions of YouTube video clips. It's actually not the videos, but actually just the screenshots of the YouTube videos, and then whichever that has like the cat in the meta information, like the title or in the description or tags. If there's the word cat, then they actually use that as a training data. So, but yeah, I could be wrong because this is all like 7 or 8 years ago, like stuff. But anyway, as you can see, so the model is doing a pretty good job of capturing the essence of human face or cat face. This words are not that straightforward. So words are actually, because words are discrete inputs. So if you have like total n number of words in your vocab, in your dictionary, then you actually, what you can do, what you have to do, or what you can only do is represent them as one-hot vectors. So still, that's what we do with words before putting them into BERT and obtaining contextualized vectors. We still have to represent them as a one-hot vector, or we actually have we assign a integer number to each word, so we can have a lookup table, and then we convert each word into an embedding, and then you actually add position embedding and semantic embedding, or like segmentation embedding on top of them, and then put them into the BERT to obtain like contextualized vectors. But before all the BERT, all the BERTs and all those kind of things came along, one hot vector was the only way to go, and just one or two simple embedding layer was what we had. So and that actually, in that case, it is hard to visualize what the model has learned for each word. We don't have like this for words. This is human face, this is cat face, but we can't easily visually represent what a word dog should look like, or what the word cat, or what the word travel, or to, diverged, would, or those are really abstract terms, so it's hard to represent them. I mean, that's also changing these days because of the vision text multimodal learning techniques, such as like VilBERT or VideoBERT or InterBERT or Uniter, PixelBERT, all these kind of stuff. So they actually they start to ground your words with pixels. So the words are not just words; they have a relationship with pixels. But back in these days, there was no way to visualize the words. But yeah, so these are one-hot encoding. So yeah, this is exactly what I'm saying. What is the representation of the word dog, or what is the representation of the word water? And because it is either just one-hot vector, which has no meaning, or either it's just embedding. You have an embedding vector, or you have a lookup vector, and then lookup vector probably doesn't mean a lot of things as well. So like, what if you can't, yeah, it's just a bunch of numbers, but bunch of like float numbers. So, and this is what actually skipgram had, or word2vec had a really huge contribution in, because we were able to actually use the word embeddings or word representation vectors and try to figure out what the model has learned. So that's what the skipgram told us, showed us that it was indeed possible to actually study the word representation learned by the model. So skipgram, as everybody knows, I'm not going to go through skipgram, but so skipgram is learning word representation using co-occurrence. So co-occurrence, which is, or also can be seen as using context. So a word is understood by its neighbors. that is the core concept of skipgram, or actually, I'm just going to call them word2vec, but skipgram actually captures better semantics than another version of word2vec, which is SIBO. So I'm just going to use skipgram examples only. By the way, if you are not familiar with skipgram, which is like really old technique by today's standards, because skipgram was proposed in 2013, if I'm correct. So if you're not familiar with skipgram, you can actually go check out my programming for AI lecture from last semester. So there's like a word embedding lecture somewhere, and so you can go, refresh your memories or study skipgram on your own. All right, so as I said, the core essence of skipgram is that a word can be defined by the words by the company keeps. So a single word doesn't have any meaning until there is a neighboring word. For example, here. So let's say that there are this is a sentence: two roads diverged in a wood. So this is actually a poem from Frost. So, but anyway. So two roads diverge in a wood, and we want to understand the word diverged, which is the target word. And what skipgram is assuming is that the word itself, the diverged word itself, doesn't have any meaning. Like, it's just one hot vector, so it doesn't mean anything. But I mean, like people understand what diverged is, but like to the computer, one hot vector doesn't mean a thing. So, but until you start considering the co-occurring words or the context. So here, these two rows in the wood, these 5 words are the co-occurring words that come with the word target word diverged. So these are the context words. So given diverged, we should be able to predict 2 rows in the wood, because a word, it can be defined by the company keeps. So if you are really familiar, if you understand a certain word really well, then you might be able to understand what kind of words would come around that word. For example, if you think about dog, then probably, like, you can think of a lot of words that could come around the word dog, like pet, cat, bark, or like toy, or food, something like that, or cute, or or bite. Like, those are the words that define the word dog. I mean, obviously, to humans, we have actually 5 senses. We have vision, we have audio, we have like touch and smell. So to us, a concept can be defined by a combination of all those 5 senses. But to the computer, with only text given, that is not possible. So what skipgram is claiming is that a word can or can be only defined by the company keeps. So given diverge, we should be able to predict 2 rows in a wood, just like what I did. Given the word dog, I should be able to predict pet, cat, bark, food, cute, whatever, something like that. So that is the essence. That is how we train skipgram, actually. So not going to go into detail with the mathematics and the equations, but basically what is happening here is that given a word, so this WT should be the target word, like diverged here. There should be neighboring words. So this would be 2 roads in a wood, like there should be a wood. So these are the word embedding. So they are actually mapped to embedding. So this is word embedding using a lookup table. So WT is actually the actual word, the diverged, and VWT is the vector representation of that word. And of course, VWT minus 1 would be a vector representation of 2 roads in a, right there, like that. And what we're trying to do is given this, we want to predict this guy, this vector, this vector, this vector, and this vector, right? So basically what you're doing is contrastive learning, just like this. Like it's a widely used loss until even to this stage, using you can see this kind of thing from all the contrastive learning objectives, like SimClear, the self-supervised image classification model. I think there was a question or chat. A question from 춘경님. representation이란 용어가 항상 추상적으로 느껴졌는데 명확히 어떤 실체를 벡터로 표현할 수 있다면 넓은 의미로 그때 그 벡터 representation 할 수 있는. 그렇죠. 네, 바로 정확합니다. 그러니까 이 벡터로 레프레젠테이션 할 수밖에 없는 거예요. 왜냐하면 컴퓨터한테 넣어줘야 되기 때문에. 그러니까 모델은 벡터를 받도록 설계가 돼 있잖아요. 우리의 모든 머신러닝 모델은. 그래서 어떤 데이터를, 실제 데이터는 이제 헬스케어 데이터일 수도 있고, 뭐 텍스트일 수도 있고, 이미지일 수도 있고, 오디오일 수도 있고, 데이터라는 건 어쨌든 다 데이터조차도 우리는 다 이제 디지털로 표현을 하죠. 이제 뭐 실제 데이터는 이제 어떤 자연 시그널이지만 그거를 사진기로 찍어가지고 픽셀로 만들어서 디지타이즈 한다던가, 음성을 녹음해가지고 그걸 샘플링해서 뭐 MP3로 이렇게 디지타이징 한다던가, 이런 식으로 다 이제 그 디지털로 변환을 한 다음에 그것도 아직은 이제 그게 이제 어떤 시그널이라고 치면은 그거를 어떤 레프레젠테이션을 바꿔야 되는데 그게 이제 벡터일 수밖에 없는 거예요. 왜냐면 우리 컴퓨터를 쓰기 때문에. 그래서 네, 그렇게 생각을 하시면 됩니다. Okay, yeah, that was a very good question. I mean, we always say representation learning, vector representation, embedding learning, or all very interchangeably. But that all comes from this motivation where you have a data and you want to represent them in a vector, because you have to you will have to feed that vector into a machine learning model. And this, yeah, as I said, before the introduction of deep learning, how people represented their vector was they came up with their features. Like, if I've told this like several times, but like, for example, if you wanted to develop a dog classifier, then you would have to actually come up with the features that indicates or that tells whether a image is a dog or not, like such as like whether there's a fur, whether there's an eye, whether there's like a tongue, whether there's like 2 sets of ears, something like that. So you would have to come up with your feature. So feature engineering was an essential part of representation, or obtaining representation. So you would program how to obtain representation. So there is actually no representation learning, because you would instruct the model what the representation should be, like exactly like here. Yeah, here. So this is, in order to represent your visit as a 40,000 dimensional vector, there was no learning. You just you defined what the representation should be, right? But then these representation was learned by the model. So you didn't tell the model what a human looks like. You didn't say that, oh, there should be like two eyes in the center, a nose in the center, and then under the nose there should be a mouth. You didn't tell that kind of information to the stack autoencoder. The model actually just learned what a human looks like by looking at millions of different images, and the cat as well. So that is why we call learning representation, and that is why the conference is named ICLR, because it's a conference of learning representation. So we no longer instruct or code representation. We learn it by using deep learning methods, which is way better than like heavy feature engineering, that what people used to do like 10 years ago. All right, so yeah, so okay, so we were talking about so visual, like once you've learned the representation of like image models or audio models, it was, especially image models, it was easy to understand what the model has learned. And now using skipgram, using this contrast learning objective, now we can see what the model has learned, or what kind of representation the model has captured for each word. And that is what we've seen so many times like this. So skipgram has captured the linear relationship between two words. And this was possible because of the concurrence information that was based on that motivated the whole learning process. So you can see that on the left side, it's all countries. And on the right side, this is all capital cities. So China and Beijing, Russia and Moscow, Japan and Tokyo, Turkey, Ankara, so on and so forth. But the important thing is, what the nations, the countries are located in all different places. So China is here, Russia is here, Turkey is here, like Portugal is here, and the capital cities are all also located in seemingly random places. Like Beijing is here, Ankara is here, Warsaw is here, like Lisbon is here. But the important thing is, when the difference between the country and its capital city is preserved, it's the same for all pairs like China, if you do China minus Beijing, then there's a vector that looks like this. If you do Russia minus Moscow, the vector again looks like this. So all the difference between the country and the capital city, the vector that captures the difference between the two, are more or less the same for all country capital pairs. That is actually that was actually a very impressive phenomenon. It was something that was not didn't think nobody thought this was possible actually, because just simple objective function that says, I want this word to be able to predict this word, and like I want the target word to be able to predict its neighboring words. That was the only objective, and then the computer started to realize there was a certain relationship between certain entities, like groups of entities, like men versus women, or country versus capital cities, something like that. And just to see this kind of thing happening was just mind-blowing, like 7 years ago or 8 years ago. So yeah, this was so this is a way to see, or to kind of get an insight into what kind of representation the model has learned. And due to this kind of interesting behavior, or this kind of interesting characteristic where the relationships can be represented as a linear operation, that actually gave us this kind of interesting examples. Like, like when you add Czech person plus the word Czech with the word currency, you would get Czech krone. If you add Vietnam with capital, you get Hanoi. If you add German with airlines, you get Lufthansa, something like this. So like this kind of linear operations, when you first saw this like 7 years ago or 8 years ago, this was like mind-blowing. Like, nobody thought this would be, because in order to do this before deep learning, you had to figure out a way to do this. Like you had to figure out what kind of features you needed to inject into the model to be able to capture this kind of linear relationship. But Skitgram, such a simple model, was able to just learn this relationship purely in a data-driven fashion, using just bunch of text corpus, just using bunch of text. And that was the beginning of representation learning of like purely representation learning of NLP or text. Right. So yeah, I've shown this example in the previous school. I mean the programming for AI class last semester, but this is also possible for, not just possible for English, but also possible for Korean. So you can see that if you add if you minus Barack Obama with United States and then plus Russia, then you will get Vladimir Putin, so which is exactly true. If you take Barack Obama minus United States plus Star Wars is actually Anakin Skywalker. That is very interesting. I don't think I've seen this example before. So Anakin Skywalker is Darth Vader. So Darth Vader could be seen as Star Wars president of the Star Wars, maybe. Anyway, so yeah, you can see that this kind of works really well even with Koreans. And actually, Skitgram works really well for healthcare as well. So healthcare meaning electronic health records. So you have a patient visit record. So let's say that during your visit, you were diagnosed with cough. And then you get prescribed the medication of benzonatate, and then you get fever diagnosis, and then you get caught with pneumonia, and then you take X-ray, and then you take the drug amoxicillin, something like this. So this would be like a sequence of medical events that happen over time when you're visiting, when you're admitted to the hospital, or maybe just over like over a few years of period of time, assuming that this is outpatient records. So when you do this, there's a sequence of codes like cough, benzonatate, fever, pneumonia, X-ray, amoxicillin, and then you can actually try to learn these concept or code representation using Skitgram. So for example, if you have a sequence of codes like this, then fever could be your target code, and then you can try to learn target codes by trying to predict its neighbors. Like a given fever, we want to be able to predict benzonatate, pneumonia, X-ray, amoxicillin, and cough. So yeah, exactly. Given fever, we should be able to predict this. And if you do this, then actually, yeah, let me click this link if this works. So I'd like to show you the 2D scatter plots of the disease. Yeah, this is an old link. Give me a second. Let's scatter plot, skip graph. Yeah, right here. So these are the disease codes or diagnosis codes learned by skipgram. And I'm not sure which data set I used to actually learn this. Maybe it was, I don't think it was Mimic. I think it was either Sutter Health dataset or maybe Children's Hospital of Atlanta, CHOA. It was, yeah, I trained this model like really long time ago, like in the early years of my PhD, but I still keep it around for demonstration purposes. So you can see that, so the colors represent a like a high level category of the disease. So like, let's take a look at some of the examples. So all the gray ones are other specified hemorrhage in early pregnancy. So you have the number here, D640.83. That is ICD-9 diagnosis codes. So they represent, and the centimeter and kilogram, that is actually not centimeter and kilogram. You can forget about it. Yeah, you can just ignore it. But anyways, diagnosis code 640.83 is other specified hemorrhage in early pregnancy, antepartum condition or complication. So it probably is something like, 이제 임신 초기에 이렇게 헤머리지가 뭐죠? 헤머리지가 피 나는 거. 한국말로 뭔지 까먹었네. 하여튼 피 나는 거를 이제 헤머리지라 그러는데, 이제 초기에 어디선가 한국말 뭔지 모르겠네. 출혈, 네 맞네. 출혈입니다. 네, 출혈. 감사합니다. 네. 이제 임신 초기에 어딘가에 출혈이 있고 그런 거겠죠. 그다음에 이거는, and this is what? This is breech presentation without mention of version. 그러니까 이거는 아기가 뒤집힌 거일 거예요. breech가 그래서 원래 이제 아기가 머리부터 나와야 되는데 엉덩이부터 나오거나 뭐 이런 게 이거 breech라고 그러거든요. 뭐 그런 거. 네. What is unspecified umbilical cord complication complicating labor. 이거는 탯줄이 뭐 꼬였거나 뭐 이런 거인 것 같고. So all the gray ones looks like it's their diagnosis codes related to giving birth, spotting, pregnancy, giving birth, something like that. So these are all the gray ones there. Let's see what the pink ones are. It's chronic obstructive asthma, cough variant asthma unspecified type, postnasal drip, acute sinusitis, maxillary sinus. Okay, so these are all related to your nose or your breathing problems. Like asthma는 이제 asthma가 뭐죠? I'm not sure. Yeah, I'm sorry. I keep forgetting what the Korean words for asthma. Asthma is 천식. 네, 천식이죠. Right. Yeah, 네, 천식 감사합니다. 네, 천식이나 뭐 이제 호흡기 쪽이나 뭐 이제 사이너사이러스면 비염이죠. 그러니까 이제 코 비강 쪽에 염증이 있는 거고 뭐 그런 것들이 이제 다 이제 요 쪽에 있는 게 다 그런 거고 뭐 네, 아무튼 그렇습니다. 네. So you can see, yeah, these are all like your breathing related, nose or asthma or something like that. The really bright green ones are angina, aortic valve disorder. This is like cardiovascular stuff. Cardiovascular system, aneurysm, aortic 대동맥이니까 이제 뭐 동맥 쪽에 뭐 이제 문제가 있고 뭐 그런 거. All right, so you can see that it is actually learning pretty well. So the important thing is, it seems to understand that certain diagnosis codes are more related to each other than the other codes. Like you can see that the color clusters here, 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 and here. And the important thing is, when training this skipgram model, nobody has told this model that certain diagnosis codes are related. You can, like, the model didn't, there is no prior knowledge, like all those diagnosis codes starting with 493 should be located together. It didn't, nobody told this model like that kind of prior knowledge. It just learned on its own by looking at a lot of examples. So we'll go back to the slides. We'll go back to the slides. So just by looking at a lot of patient visit records, it just picked up that certain codes are related, certain codes are more related to each other, and that actually enabled us to draw that kind of like interesting scatter plot. And you can do actually with that learned representation, you can do linear operations just like you did with the words in your with the word vectors using skipgram. So here, let's see what's, so this is just finding the most closest code of the given. So given like, for example, given this acute upper respiratory infections, D465.9, given this code, what is the closest code or closest code vector, code representation, in terms of cosine similarity? So in terms, and we have like 3 groups. We have diagnosis group, we have medication group, and procedure groups. And you can see that the closest diagnosis codes to acute upper respiratory infections are bronchitis, good enough, cough, acute sinusitis, bronchitis, pharyngitis. So these are all related to like your lungs or your nose or your or your pharynx or larynx. And this is actually should be close to acute upper respiratory infection. So respiratory infection is 호흡기 쪽에 이제 감염이 됐다는 거니까. And the medications, I'm not sure if these are the medications usually used to treat this problem, but I'm gonna assume that it is true. And the procedures, if you have some respiratory infections, usually, I guess you have to measure your 산소 포화도. I'm not sure. Like, yeah, usually if you have like a breathing problem, then you can't actually produce your body system with enough oxygen. So you have to measure your oxygen, how much oxygen is resolved, is contained within your bloodstream, something like that. Chest PA, so it's X-ray. So if you have something with your lung problem, if you have a lung problem, you usually take X-rays. So same with the diabetes. The closest ones are another diabetes, hyperlipidemia, 고지혈증. So you have a lot of fat in your bloodstream. abnormal glucose, 그러니까 혈당에 문제가 있을 수도 있고요. 뭐 이제 비만, 뭐 그런 것들. 다 그 당뇨랑 문제가 있는 것들, 관련이 있는 것들이죠. 그다음에 이제 뭐 글루코스 블러드스트림, 리시노프릴 이런 것, 사실 뭔지 잘 모르겠어요. 리시노프릴이 뭐 실제로 이거를 뭐 트리트한 약인지는 모르겠고. 그다음에 이제 당뇨가 있으면, 당뇨가 보통 이제 눈이 멀거든요. 이제 당뇨가 심해지면. 그래서 뭐 눈을 뭐 체크업도 하고, 그다음에 이제 뭐 당뇨에 대한 교육도 하네요. 그다음에 이것도 안과, 옵살몰로지가 안과니까 이제 안과도 한번 가보고, 뭐 이런 것들이 다 이제 관련이 있는 코드들이다. 뭐 이것도 테어필름 insufficiency, 테어필름 뭔지 잘 모르겠어요. 테어필름, 이 눈에 어떤 그 각막이 이렇게 찢어졌다거나 뭐 이런 것 같은데, 그래서 글라코마, 이제 뭐 캐터, 뭐 백내장, 녹내장 이런 것들이 그래서 나오나 보네요. 그다음 뭐 안경을 맞춰주기, 뭐 리프렉션, 이것도 이제 뭐 회절, 이거 아마 눈 이렇게 초점 이렇게 눈이 뭐 이렇게 뭐 잘못된 거 맞추는 뭐 검사하는 그런 거인 것 같습니다. 뭐 비주얼 필드니까 이제 시야 이렇게 이그잼 하는 것들 다 뭐 이런 거랑 관련이 있을 수 있겠죠. So it looks like everything is like, you know, it looks like the skipgram applied to healthcare is correctly capturing the relationship between relevant codes. So these are looking for closest codes in terms of cosine similarity. And you can actually do like disease additions. So if you add hypertension with obesity, what's the closest one you get out of this operation? And you can see that these lead to hyperlipidemia and diabetes and coronary atherosclerosis. So 그러니까 하이퍼텐션은 고혈압이고 이건 비만이니까 고혈압이면서 비만인 환자가 이제 누구랑 가장 가깝냐 보면은 고지혈증 환자나 아니면 이제 당뇨 환자나 동맥경화 환자 이런 분하고 제일 가깝다. 이제 뭐 또 뭐 아니면 하이퍼텐션 당연히 하이퍼텐션하고 가까울 수 있겠죠. 그러니까 이제 굉장히 이제 이거를 잘 캡처를 하고 있죠. 이런 거랑 이런 게 있으면은 요런 거랑 제일 가깝다. 그다음에 fever랑 cough 그 열이 있고 기침이 하고 있으면은 뭐랑 제일 가깝냐? 폐렴이다. 또는 기관지염 또는 뭐 아까 보셨던 호흡기 감염, 뭐 기관지염, 뭐 비염 뭐 이런 것들이랑 가깝다. 그러니까 굉장히 아주 잘 캡처를 하고 있죠 생각보다. 그러니까 이제 열하고 커프를 따로따로 하면 이제 약간 다르겠지만 이게 둘을 더하면은 얘네들이 가깝다는 거. 또 그다음 비주얼 디스터번스 그러니까 뭐 시야가 잘 안 보이는 거랑 이제 눈 근처가 아픈 거를 보면은 이제 아까 봤던 이제 뭐 각막이 찢어졌다거나 아니면 뭐 이런 것들. 아스티그마티즘 뭔지 잘 모르겠네. 프레스바이오피아가 아마 뭐 그게 원시나 근시나 둘 중 하나일 거예요. 뭐 잘 모르겠는데. 네. Loss of weight and anxiety state. 그러니까 요거는 이제 살이 빠지고 아 불안해, 불안증이 있습니다. 그럼 뭐냐? 그럼 이제 우울증이다. 이것도 이제 굉장히 성능이 잘 되죠. 이건 이제 그 만성 피로. 요거는 이제 불면증. 이거는 그냥 anxiety disorder. 이건 esophageal reflux. 이거는 이거 역류성 식도염인데 왜 이게 나온지 잘 모르겠어요, 사실. 네. 근데 어쨌든 처음 네 개는 이제 굉장히 잘 된다. 네, 보실 수가 있습니다. So you can see that the just simple skip round with combined with large volume of electronic health records is enough for the model to capture this kind of interesting linear relationship between the codes. Right. So that is the essence, but you can actually develop this to actually further to make a further specialized model for electronic health records, which is actually we've took a look at this electronic health record structure, the two-layer structure, where we thought initially the predictive model we thought that this was the norm, like we have a timeline and then the medical events occur one time at like one medical code occurs at a time, but this is not exactly true because actually this is a two-layer structure. So EHR has a visit level structure, a visit level layer, and then there's a code level layer. But this is actually pertains only to outpatient records. So 이건 외래 환자에 대한 특화된 얘기이긴 합니다. 왜냐하면 이제 외래 환자 같은 경우는 한 번 병원에 가면 여러 개의 코드가 발생하고 그 코드의 순서가 사실 애매하거든요. 그러니까 보통은 뭐 진단을 먼저 하고 그 다음에 이제 약 처방하고 뭐 수액을 맞고 하는데 꼭 그렇진 않아요. 그러니까 이제 항상 그런 건 아니고 보통은 뭐 이제 이게 의심돼 가지고 뭐 내가 이 사람이 뭐가 있을까요? 뭐 폐렴이 의심되니까 죄송합니다. 폐렴이 의심되니까 엑스레이를 찍어보고 그 다음에 폐렴의 진단을 한다던가 뭐 그런 식으로 되는 경우도 있기 때문에 이제 정확하게 그 어떤 순서가 이게 명확하지가 않습니다. 외래 환자 같은 경우. 그래서 이제 이렇게 원샷으로 셋으로 나타내는 게 조금 더 자연스럽고요. 근데 우리가 그동안 했던 ICU 스테이 같은 경우는 명확하게 이게 타임 스탬프가 있잖아요. 이 사람이 이제 언제 들어와서 몇 날 며칠 몇 시 몇 분에 뭐가 있었고 이게 정확하게 시간이 쫙 있기 때문에 그거 같은 경우 이제 쭉 그냥 시퀀스로 처리하는 게 편한데 이제 외래 환자 같은 경우는 꼭 그렇진 않다. 그래서 이제 외래 환자는 이렇게 set of code의 시퀀스로 나타내는 게 좋다라고 말씀드린 겁니다. So just like I said in Korean, this only pertains to outpatient records, where outpatients are the patients who go to the hospital and then just get diagnosed and treated, and maybe there's like a couple procedures involved, but it's usually just one shot thing. So you go to the hospital and then you leave the hospital within like 10 or 15 minutes. So it is usually hard to distinguish or to assign certain sequence to the codes that occurred in your outpatient setting. Unlike the ICU stay. So because in ICU stay, we actually saw that all the medical events have a specific timestamp from like day, hour, minute, like you have a specific timestamp and then you can just simply lay them out in a sequential order or temporal order and then feed them into RNN. But that was ICU stay, and in the outpatient setting, not so much. So we're going to assume that this is our outpatient two-layer structure of EHR. So skip-ram, we took fever and tried to predict benzonatate, pneumonia, chest x-ray, cough, and amoxicillin, but that doesn't actually represent the actual structure of EHR. So what we're going to do is we're going to, again, capture the sequential relation and the code co-occurrence relation. So we have to capture the two at the same time, just like we did with the retain. with the visit level attention and the code level attention. We have a code level relationship to capture and the visit level relationship to capture. So this is a Med2Vec model architecture. I won't go into the detail, but the important thing is that it's a 2-layer thing. So there's a multi-hot vector, which represents multiple codes occurring at a single visit. So this is the XT is the teeth visit representation in sparse binary high dimensional vector. And then you embed them into a lower dimensional space using ReLU activation. So this is important. The reason for using ReLU activation is to maximize interpretability, so which we'll see in the later slides. So once you have them, then you have a visit representation, and so this would be the code representation, and then you concatenate them with demographic information such as like ethnicity, age, gender, marital status, something like that. So you can either, I mean, you can do it if there are demographic information. But if there is no demographic information, then you can just leave them out. And then you roll them again. You roll them again into the visit representation. So this is a 2-layer structure. And then given the visit representation VT, you should be able to predict neighboring visits. So it's no longer neighboring codes because you have a sequence of visits. So you should be able to predict neighboring visits, but each visit can be represented as a multi-hot vector. So this is xt minus 1, t plus 1, t plus 1, t plus 2, t minus 2. So these are all the same sparse high dimensional binary vectors. So given VT, we want to predict these neighboring sparse vectors. So that's entirely it. So yeah. So training, yeah. So there is no equations or anything, but you can assume what the equation would be. That the code level equation should be exactly like Word2Vec, and then the visit level objective function should be just softmax for neighboring visits, and that's it. So that you just add those two terms together. And so yeah, the training learning from visit level information, we are trying to leverage the sequential information. So given a visit, we can predict the patient's past and future, which is reasonable assumption. And then, so visit is a moment in a patient's continuous clinical experience. So patients like physiological state flows continuously along the time axis. And when you visit a hospital, when you are an outpatient at a hospital, then you're actually showing a snapshot of your physiological state at certain points. So given that, we can probably predict your past and future. So yeah, train VT to predict medical codes in the past and future visits. So yeah, just like this. So this is that part. And then the code level information is straightforward. We're just going to use skip param. So but we're going to actually learn a non-negative representation of codes. So that is why we use the rectifier linear unit ReLU activation function. So the reason for learning a non-negative representation of codes is to make it interpretable. So we can understand what each coordinate captures. So coordinate meaning that, for example, if UT here is 128 dimensional vector, which is human defined. If this is a 128 dimensional vector, then we want to interpret what each dimension represents, what each dimension is trying to capture, just like which was not done before with the Word2Vec or anything like that. So Word2Vec only show that the words have a relationship, like linear relationship, and you can do like plus and minuses to do interesting stuff. But what in this model, what we are trying to do is to study what each dimension of your word, your code vector or your latent space is representing. So that, and in order to do that, we want our representation, we want our latent space to only have non-negative values, because if we have plus and minus values, then it is hard to interpret what each dimension means. It should only have 0 to infinity, so that if certain dimension has like a really high value, like 100 or 200, then that means that dimension is activated and we can understand what's going on. So yeah, yeah, this is simply just just an example. Like if your visit consists of 1, 2, 6 codes, 2 diagnosis codes, 2 medication codes, and 2 procedure codes, then you actually take turns to predict given one target. Given one, you select one target and then try to predict the others, and then you select another target and then you try to predict all the others. Like you just do a for loop. So like in the for loop, like number 1, this is the target, and then for loop number 2, this is the target, and this is target, this is target. You just go over the entire codes. I think there was a question. Is it neighboring visit symptoms or something else? Neighboring visits are actually everything, because a single visit can consist of diagnosis codes, medication codes, and procedure codes. So the neighboring visits would also consist of diagnosis and medication procedures. So it's just all the things that could happen at a visit. So you're trying to, given the visit vector VT, you're trying to predict a multi-odd vector, or so it's a multi-label prediction setting, basically. So in this setting, you have a VT, which is an embedding, and then you have a multi-odd vector, like 1, 2, 3. Let's just say that your window size is 2. So you look at 2 previous visits and 2 future visits, and given VT, you want to predict you want to do a multi-label classification prediction for this visit, and this visit, and this visit. So you would have like 4 terms. So yeah, that's basically it. It's a very simple setting. And using this, so we've trained the METAVEC model using the data set provided by CHOA, which is Children's Healthcare of Atlanta. There were a lot of patient records, so about 500,000 patients, and the number of visits was 3.3 million visits, so a lot of data. And then the feature space was 28,000, or actually more or less like 30,000. So 10,000 diagnosis codes, 13,000 medication codes, and 5,000 procedure codes. And average codes per visit. So like these are all outpatient settings. So average codes per 1 outpatient visit is about 8. So there are about 8 codes. Like here, this is 6 codes, but there are usually 8 codes per visit. So you have a lot of co-occurrence relationship to learn from. And yeah, so once we've learned the so when you have METAVEC, you can obtain 2 things. One is UT, which is the code representation, and the VT, which is the visit representation. So given the visit representation, we can do some interesting predictions like CRG prediction. So CRG is like it determines, it's an indicator for how complex your state is, like whether you're just having a normal cough or fever, that's like non-complex. But if you have like really congenital disease or like a hereditary disease or like genetic disease, then that's a complex case. So it's a binary classification. Or a future code prediction, you can also do like what kind of diagnosis you would receive in the future given the visit representation. But yeah, but I'm not going to go into detail because these are actually just more or less prediction tasks. But the interesting thing is actually the interpretability and the representation that the model has learned. So we'll just quickly skip through the details. So this just means that compared to the baselines, like baseline being the logistic regression, stacked autoencoder, skip-gram vectors, and glove vectors, compared to those, METAVEC actually outperforms all the baselines for the 2 prediction tasks, the CRG prediction and the future code prediction, for like across a diverse sets of hyperparameters. But this is more or less actually straightforward. Scalability, like how much training time you require, but this is also not that much of an interesting thing. The interesting thing is this. So we've actually briefly took a look at this example when we were studying retain, the interpretable model. So if you remember, in retain, there were 2 coefficients that was dynamically generated, which was alpha for the visit level attention and the beta for the code level attention. And if you remember, alphas were scalars and betas were vectors. And that's when I showed you guys this example here. So here, this is a code so once you train METAVEC, you have a UT, the code representation, code representation vectors. So, and assuming that maybe we define the code representation vectors. So I'm just going to show you guys again. Here, let's assume that we've set this to be 256 dimensional vectors. And we can see that now what we're trying to do is we're trying to study what each dimension is trying to capture, because these these multi-hot vectors, these binary sparse vectors are just exactly like one-hot vectors, except that there are multiple ones here because multiple codes can occur at the same visit. But aside from that, this is exactly like one-hot vector. So one-hot vector doesn't have any meaning. It's just an indicator for different codes. So by studying this dimension here, you can see that if like this dimension could represent cough, and this dimension could represent fever. This dimension could represent like respiratory disease. Like this like each dimension has its own meaning, and that actually represents very low level features, because for example, like the scatter plot you guys just saw, that captures high level meaning. Like similar codes are clustered around each other, so that actually captures some high level semantics, like diabetes and obesity are closer to each other, or respiratory disease and bronchitis are related to each other, something like that. So, but if you look at the one-hot vectors, you can't really capture it. You can't learn that kind of information. So that is why we're trying to look at the code representation vectors dimension and see if each dimension captures a higher level semantics. So we can actually see that we can see the interesting things happening here. So if you look at dimension 112 or coordinate 112 of your 256 dimensional vector, and we rank the codes. So there are how many codes? There are 28,000. So there are 30,000 codes. So given 30,000 codes for this particular dimension 112, we rank all the codes, all the 30,000 codes, in the order of the strength of the codes that strength of the value in this coordinate. So kidney replaced by transplant, this code had the highest value in coordinate 112. So I don't know, I don't exactly remember what kind of value this had, but maybe it had like 10 and like maybe 9.5, 9.3, 8.7, something like that. So, and if you rank them by their strength in this coordinate, you can see that these are the prominent ones. And as I said, these are all related to sickle cell disease. 겸상적 혈구 얘기 저번에 했었죠. These are all related to sickle cell disease and something wrong with your bloodstream or red blood cells. So that is why you have red blood cell count here. Heart transplant, sickle cell disease, bone marrow는 이제 bone marrow가 뭐죠? 골수죠. 골수 같은 거를 옮기거나 뭐 이런 것들이 다 이제 이쪽에 해당이 됩니다. 이제 적혈구를 만들지 못한다던가 무슨 혈액에 문제가 있다던가 이런 거 다 이제 이쪽에 몰려 있는 겁니다. 그러니까 이제 이 112번 디멘션은 그런 것들, 그런 하이 레벨, 그러니까 얘네들 하나하나는 다 관계가 그러니까 얘네들 하나하나를 원핫 벡터로 나타내면은 전혀 관계를 알 수가 없는데, 이런 식으로 코디네이트 112의 랭킹을 세워보니까 얘네들이 전부 다 관련이 있더라. 그리고 112는 이런 세만틱, 그러니까 이제 혈액에 대한 세만틱을 캡처하는 디멘션이더라라는 걸 알 수가 있는 겁니다. So that's what I'm trying to show here. And coordinate 152, as we've seen before, coordinate 152 represents all the codes, all the medical concepts related to breaking your bones because of athletic activities or working out or doing sports. So X-ray knee, X-ray thoracolumbar. I'm not sure what this is. Something related to thoracic. So this is like 흉부나 가슴 쪽에 이제 엑스레이 찍는 것 같네요. 네. 이제 무릎 엑스레이, 흉부 쪽 엑스레이, 그다음에 이제 이 공공 건물에서 사고가 있었습니다. 체육을 하는데 체육 활동을 하는데 이제 문제가 있었던 것. 사람이나 물체에게 맞은 것, 이런 것들 다 이제 그러니까 어떤 이 몸을 움직이는 액티비티를 했을 때 이제 부러지거나 맞았거나 상처가 있거나 그런 것들은 전부 다 152번이 이제 그런 것들을 캡처하고 있는 거예요. 152번 차원이. 이제 각 차원이 다 하고 있는 일이 있는 겁니다. 이제 112번 차원, 152번 차원. 사실 어떤 차원은 약간 좀 이제 이게 덜 드러나는데 대부분의 차원이 굉장히 잘 드러나고 이제 이것들은 제가 몇 가지 그 피킹을 한 거예요. 이제 특히나 잘 드러나는 것들은. 그래서 이제 각 차원이 다 맡은 역할이 있고 그 말은 우리가 이제 이 비전 쪽이 이미지 쪽을 이제 비주얼라이즈 할 때 사람의 얼굴, 뭐 고양이 얼굴 비주얼라이즈 하면서 이제 이 모델이 요런 레프레젠테이션을 배웠구나라는 걸 알 수 있었듯이 멜투백을 보면서 이제 이 모델이 이 벡터를 배울 때 어떤 의미로 배웠구나. 이제 112번이 강하면은 그 벡터는 112번이 강하게 발현되면은 그 인풋은 요런 쪽의 의미, 요런 쪽에 어떤 관련이 있겠구나. 그다음 152번의 이번 차원이 강하게 발현되면은 이 코드는 아마도 어떤 뭐 액티비티나 뭐 뼈가 부러진 거 이런 거랑 관련이 있겠구나 하고 이제 이게 실제로 인터프리테이션이 어느 정도 가능해진다는 겁니다. 이제 그게 이제 밸류 때문에 가능해진 거고 이게 밸류가 아니었다면은 이게 플러스에서 마이너스까지 이제 그 밸류가 가질 수 있기 때문에 이제 플러스 10의 밸류를 가지는 코드와 마이너스 10의 밸류를 가지는 코드가 어떤 관계가 있는지 약간 알기가 좀 애매하거든요. 근데 지금 이게 밸류를 썼기 때문에 각 차원에서 가장 낮은 밸류는 0일 수밖에 없고 가장 높은 밸류는 물론 뭐 무한대겠지만 무한대는 없으니까 그냥 이 그 밸류 순으로 랭킹을 했을 때 이제 굉장히 극명하게 이렇게 드러나게 되는 겁니다. Alright, so yeah. There are some more coordinates, like 142 is all related to I'm not sure. It's something related to your brain. Subdural hemorrhage. 그러니까 이제 뇌출혈이나 뭐 mental disorder, hearing loss, 뇌막염인가요? 뇌막염? hearing loss, intracerebral, 그러니까 뇌출혈, 뭐 그런 쪽이니까 뇌 쪽에 뭐가 뭐 출혈이 있거나 문제가 있는 게 다 이쪽이네요. And coordinate 14182 is pain in joints. Okay, so it's a pain in joint in your shoulder, pain in joint in your leg, your foot, your actually multiple. So these are like senile diseases, I would say. Pain in joint, MRI brain, other joint derangement, yeah, all the joint problems. And coordinate 190 is all related to Down syndrome, congenital anomalies, autosomal deletion. Autosomal deletion is like related to your genes, 유전자, 염색체 관련된 거고요. Another chromosome related stuff, acquired hypothyroidism. Yeah. So I would say these are all like, genetic or hereditary congenital disease. 그러니까 이제 날 때부터 타고나는 질병들 있잖아요. 그 유전적으로. 그런 것들이 이제 190번에 전부 다 캡처가 되고 199 is infantile cerebral palsy, congenital quadriplegia, dysplasia. So this is 마비 쪽인 것 같네요. 뇌성마비나 이런 것들 이제 손발을 잘 가누지 못한 것들이 전부 다 그쪽인 것 같습니다. 네. So 199 is all related to not sure what 뇌성마비 is in Korean. I mean in English. Like palsy itself is like a name of a disease. I'm not sure how to say it otherwise. Anyway, so yeah, these are all really like not being able to control your limbs really well. These are all related to that kind of diseases. So yeah. So 112, 152, 141, 182. Important disease related to patient complexity, and 19. These are like disease group that maximize complexity prediction probability. These are actually, I've written this because this actually has a high correlation with the CRG prediction. The CRG prediction was like complex or non-complex disease classification. So some are related to complex disease, some are not related to complex disease, but no need to bother. But the important thing is this can be done with a carefully designed embedding training model. All right, so conclusion is that it learns efficient code visit representation and interpretable. And I would say this is the important part, interpretable part. So the whole motivation behind this class was we wanted to like learning representation is the essence of deep learning, but some are easier to interpret than the others. Like for example, like like human face or cat face, those are easier to visually understand what's going on and what kind of representation the model has learned. But it wasn't so much the case for discrete inputs such as like words or medical codes, but by using skikgrams or MetaVec, there is a way to gain insight into what kind of representation the model is learning, which is not really like directly visible, like visualized like human face or cat face, but still there are some like clever ways where we can poke around and try to understand what the model is capturing. So that was the essence of this class. All right, so this is the end of the class, and next week we'll look at the how to learn better concept representations using domain knowledge and graphical knowledge. So that would be, and then after that, then we'll go to the next project number 2, actually, which will be the which would be the text classification, actually. All right. If there are no more questions, I'll see you guys I'll see you guys next weekend. I mean, next Tuesday, and have a good weekend. And as I said, if you have questions or like any kind of comments or feedback related to project number 1, please let me know. All right. Bye bye, everybody.